So we're going to go ahead and do the next video. Just want to kind of clarify some things about how you find a hypothesis and how you interpret that p-value. So let's kind of go through this. All right, so in a hypothesis test, essentially what the hypothesis test is it's a statistical way to evaluate a claim that's being made by a company or another person. So if somebody like claims something, say that a car gets 32 miles per gallon, there has to be a way to verify that. So that's what we use as the hypothesis testing. So every significance will test or ask basically, is our statistic different from the parameter due to chance, or is it different because the claimed parameter is not correct? Because if you think about it, we know every time we pull a sample that sample value is going to vary. It's not going to be the exact value of what the parameter of what we know is going to happen. So every time we pull a sample, it's going to be different. So what we have to figure out is it different enough, so to say, that it's because the parameter's not right, or is it just different because it's a sample? There's differences in change in that variation. So the basic test has three pieces to it. So you're going to establish your hypotheses, you're going to calculate your evidence, and then you're going to use the evidence to make a conclusion. Now, we're not going to focus a lot today on how to calculate the evidence. We'll do that in the next video when we put the whole hypothesis test together. Today, I just really want to focus on how do you get the hypothesis and how do you interpret the evidence that you're given. So first thing is establishing the hypothesis. So we said HO is that the claim is true. So it's always going to have an equal sign. HO is what we call our null hypothesis. That's N-U-L-L, our null hypothesis. And then HA is our alternative. It basically is what we say is okay if HO is wrong. So it's always going to have an inequality sign to it. So we're always going to have one of these values here. So it's always going to have either a less than, a greater than, or a not equal to sign with it. So that's going to be able to help us figure out how, what direction our alternative or how the data is really, what's really going on with that data. Okay, so an example to kind of give you an idea. A medical researcher is interested in finding out whether a new medication will have undesirable side effects. The researcher is particularly concerned with the pulse rate of patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after the patient takes the medication? The researcher knows that the mean pulse rate for the population under the study is 82 beats per minute. It is 82 beats per minute. This right here, that is going to define our HO. It's going to tell us that HO is that 82 minutes. Now, is this a proportion or a mean? Well, it says the mean pulse rate. So that means that we're dealing with mu here, not our P. We're dealing with a mean. Okay. Now let's go back up and see what else it's asking. Will the pulse rate increase, decrease, or remain unchanged? So that kind of sounds like we don't know what it's going to do. So that's going to signify just a change. So that means that we don't know. So we're going to say it's not equal to that value. So the hypothesis, our HO is mu is equal to 82, and HA is mu does not equal 82. All right. A chemist invents an additive to increase the life of the automobile battery. The mean lifetime of an automobile battery without the additive is 36. So why don't you pause for a second, write down your answers for the hypotheses, and then come back. Okay, so let's kind of go through. The mean life of an automobile battery without the additive is 36 months. So we know then that our HO is that it is 36 months. Okay, so what is that HA? So the chemist invents an additive to increase the life of the battery. Increase. So increase means that 36 months should last longer. So it should be a greater than. All right. C. So go ahead and pause the video again, let you read it, and then we'll come back together. All right, so a contractor wishes to lower heating bills by using the special type of insulation in homes. If the average of monthly heating bill is 78, her hypothesis about heating costs with the use of insulation are, all right, so what do we know? Heating bill is 78, so that's HO, right? And they want to lower the heating bills. So lower would mean that this would be a less than. So HO is equal to 78. HA is that it's less than 78. Now, if you notice in this case here again, we're using mu's and not p's. Why? Because we're talking about an average amount. So you really got to look at what that value is to find out what that parameter is that you're looking for. Okay, so now that we know how to set the hypothesis values, in the last video, we also talked about this idea of a p-value. So what is it? Well, the p-value is basically your evidence against HO. Okay, so it's the probability of getting a value equal to or more extreme than what we observe if HO is true. Okay, so if the things are what they say they are, it's the probability we're going to get a sample that we get. Now, that's how we're going to make, or how we make our decisions. So if the P is greater than alpha, we fail to reject. We never, ever, ever accept the HO. You never accept the HO. Okay? Never accept the HO, right? It's always a fail to reject. I know it seems like it's just a terminology, but it's very important because we're not guaranteeing that it's right. We're just saying we don't have the evidence at this moment. And then if P is less than alpha, we reject the null or reject HO, reject the HO. Okay. So if the P is low, you reject the HO. Okay. P is low, you reject the HO. For rejecting HO, that means, well, we have to do something else. So we're going to have to accept whatever the alternate is. So we accept whatever HA is. So if you reject the HO, you accept HA. You notice we've got this little thing right here. This is what we call alpha. So what is alpha? So alpha is basically what we call our level of significance. It's what we compare things against. So it's our threshold point, if you want to say. It's saying, hey, if a value is less than this, if it happens, then that's not okay. That means that what we were told is not correct. So usually the alpha that we use is 0.01 or 0.05. Now, most problems will give it to you, but sometimes they won't. If they don't give it to you, the business standard or what we normally use is 0.05. So remember, if the P is low, less than the alpha, the HO must go. The P is low, HO must go. All right, so how do you interpret what that p-value is? So this is kind of like a sentence that you can use, a fill-in-the-blank sentence, to actually interpret it. So it's assuming that the null hypothesis, in context, is true. There is a p-value probability of getting whatever value you got or more extreme by chance. So let's kind of give that a try. So Claire and Anna Rose have a disagreement about whether or not 1 in every 4 students at their school had played in the rain. Anna Rose believes that the value is too high. When they surveyed a random sample of 80 students, 12 reported that they had played in the rain at least once. The appropriate test was performed and they obtained a p-value of 0.0194. State the appropriate hypothesis, interpret the p-value in context, and what decisions should be made. So I want you to pause the video and try those out and then come back. All right, so welcome back. Let's go ahead and figure out what the appropriate hypothesis. So the appropriate hypothesis there would be that HO is that P is equal to 0.25. Now why P? Because we're looking at a proportion. It's 1 in every 4. So 1 in every 4 would be 0.25. And HA, well, Anna Rose believes that value is too high. So that means that our HA then is that it is less than that value. Okay, what about our interpretation? Interpret the p-value. So assuming that the true proportion of students at the school that have played in the rain is 0.25, there is a 0.194 probability of getting 0.15 or more extreme by chance. So where did this 0.15 come from? Well, it came from our sample. When they surveyed a random sample of 80 students, 12 reported they had played in the rain at least once. So 12 out of 80 is 0.15. And finally, what decision should be made? Well, P is 0.0194, and they don't give us an alpha, so we're going to use that 0.05, so we're going to reject HO. We have enough evidence to say that less than 25% of students at this school have played in the rain. So that kind of gives you the overview of what we're looking at. We'll put the whole test together tomorrow. I'll see you guys later. Bye-bye.